Thank you. Well, how to start this? Here I'm going to present you how we actually use this concept of dynamic forward slicing for solving the problem of dynamically replanned multi-drone mission. Yeah, there is a lot of keyword here, so first a bit of context. What is a multi-drone mission? A multi-drone mission is a type of operation that we use a lot of drones to achieve a certain goal. That is the oversimplified version of it. In particular, we're using this for the Health Drone project. We are delivering several diagnostic sample and medical supplies across, well, simulating cities. I mean, it would be nice to have actual drone for this, but for now it's everything simulated. And this is how more or less you can see as a multi-drone mission. You have several drones moving to different places. In particular, because of the project that we're working with, they are moving with a purpose. They are actually carrying something to these locations. And because we are, DSL guys, we develop a DSL for operators because of all the reasons that we already know about DSLs, right? So we developed this DSL, and the program that you see at the left is actually, that program in the left actually yields the flight path of each drone on the right. But we are working in a heavily dynamical environment. Anything could happen. For example, an emergency helicopter might decide to fly across one of the flight paths of the drone, and we don't want a drone to crash an helicopter, especially an emergency helicopter. So what we need to do is to actually try to avoid this problem. So as a simplified version of the previous mission, we have this other one where we have a drone moving to certain locations, and then when the drone has to arrive to the last location, something in the environment happens, and they don't have to avoid that red area. One possible solution about this, I mean, what we want to do is to avoid any risk. So one possible solution is, okay, let's restart the mission. Let's take the same program that we have, the same parameters, and let's compute the flight path again. But that is actually not replanning, that is restarting the mission. We are going to start over again, and we're going to visit the previous points that we already have visited. And we don't want that. What we want actually is to calculate a new path from a certain point from a certain point to the future. And what we actually thought about this is, instead of restarting the original mission, is just we create another program. We generate a new program that takes certain consideration from the original program that is actually consider all the different circumstances that the drone has to avoid. Why this? Because we don't know how to write planners. I mean, we are DSL guys, software engineering guys. Writing planners and replanners is not an easy task. So, but we already have a planner, and we wanted to reuse that planner to solve the problem of dynamically replanned missions. So what we did is to originate a new program, to generate a new program from the original program that keeps the goal of that program from a certain point of execution. And to do that, what we did is to work with all the statements of the original program. In particular, we remove all the irrelevant statements. And for that, it came to our attention that we can use this program slicing technique. In particular, using dynamic forward slicing. Just as a quick reminder, that is because when we have one particular statement of interest with program slicing, what we can check all the program and check all the statements that affect this statement of interest or are going to be affected from this point of execution. So basically, we can see the past and the future of this statement. And we use forward slicing because we only want the future, and dynamically because we're using the runtime state of the program. So then we take this program and we put this into a planner that we already built in a previous work, and we dynamically replan them. So in this talk, I'm not going to talk about the planner itself. I mean, it's not a big deal, but if you want to know more, we have previous papers about that. What I'm going to talk about in this talk is about how we use dynamic slicing, how we generate this new program according to certain rules. Yes. But well, that was the context. But now we need to know a bit more about the DSL itself that we built. This .DSL. .DSL, the drone operation template specification, a DSL to define multi-drone missions. No more than that. This is a typical DOTS program at the right. You can see a lot of statements, typical for loops or a lot of particular domain interesting statement for the case of multi-drone missions. But in the case of this talk, we're going to focus more into the AST. So it's going to be easier for us to understand how we do the slicing. We have a lot of different statements in DOTS, but I think one of the most interesting one is that actually DOTS allow drones to behave accordingly, but also DOTS allow for the specification of how drones are going to move within themselves, something that we call coordination of actions. In particular, we have two interesting ones, the sequential and the parallel statements. Of course, they are the names are quite specific, but just to be sure, the sequential statements in this case is going to execute every statement sequentially, but that means that, for example, DS1 is going to move to location L1, and only when that drone arrives to that location, DS2 is going to start moving. And parallel, we're going to move every drone in parallel, right? Well, as parallel as possible, we have something very similar data races here. We cannot move the same drone to different locations at the same time. I mean, it's physically impossible. We also have for loops, so we are allowed to, instead of writing a lot of move to one place, then to another, we just put everything into an array of locations, and we iterate over this array of locations. In this case, this is a parallel for loop, but we only have one physical drone. So how we actually do a parallel for loop for real? We extend the loop construction to support an array of drones, which means we're going to visit every location N in NS using as many drones as possible presented in DS. And that is DOTS. So the idea now is how we actually achieve this dynamic, how we generate this new program by slicing DOTS. And that's what we want. We want to transform the original program to a new one to dynamically replan missions. For that, we're going to use the AST example, and I'm going to color the AST. Green statements or green nodes in the AST actually means that the program has already executed those states. Red nodes mean that the program is executing those states, those nodes, and green and yellow nodes are nodes that still has not been executed in DOTS. So how do we slice DOTS? Well, we apply several rules. In particular, we remove executed nodes. We remove every green node from the AST. Those nodes already have been executed. We don't want to restart the mission. We keep yellow nodes as they are. They are the future of the mission, and we need to complete them at some point. So in particular, we just focus about the red nodes. What we do is to take every executing node in the system, and we transform the AST according to these red nodes. And for that, we actually have to define a transformation for every statement possible in DOTS. Time constraint, I'm not going to explain every statement, everything is in the paper. However, I'm going to explain the most interesting one, which is action call and coordination statements. Action calls in DOTS are a way of making drones do something. And the slicing of this is actually depends on the action itself. We cannot make a generic explanation for every action in the system. Here we have, for example, this straight action, which allows a drone to move to a certain location. And what is the slice of that straight action? It's actually the same action. The drone is moving to a point L. We want the drone to keep moving to that point L. Of course, there is a new initial position of the drone that takes into consideration, that the planner takes into consideration. We also have this patrol action, which is no more than the drone is going to cover a geographical area. And what is the slice of this? Well, covering a geographical area is no more than going for every vertex. So what we do is remove every vertex that the drone has already passed, and the vertex that is still are missing, we just put them into a sequential statement. So basically, what I want to say here is that action calls, the slicing of action call depends on the action itself. If we want to add more action into the system, we have to define a new slice for that action. If we want to have, of course, dynamical replan of that mission. Coordination statement, well, the sequential is very easy. We remove the green ones, and that's all. We are sure that that is going to work because the sequential statement, only one statement inside that is going to be executed at a time. It's quite simple. And of course, we define the slice as a recursive function. So we need to actually slice every red statement inside that sequential. But because the straight action call, the slice of a action call straight is the same action call, so it actually stays the same in this example. The most interesting one is actually a parallel statement. That is because any statement inside that parallel statement could be executed at a time. And we need to ensure some level of safetyness on this. How do we do this? We put first every executed node in another statement called prioritized statement, and we put those at the beginning. And then we take the original parallel statement with only the yellow nodes, and we put that at the end of that prioritized statement. The prioritized statement is another type of coordination similar to parallel, but it's gonna execute in parallel starting from the first statement. So prioritized statement is gonna be sure that D2 going to P2 is gonna be executed first, then D3 going to P3 is gonna execute second. That is how the prioritized statement works, and that's why it works. If we put everything into a parallel statement, for example, we cannot be sure that the first statement are going to be executed first, and that means that a drone that was flying before, it may be stuck into the air doing nothing, and safety is the name of the game here. And actually, the most difficult one is the for loop. It was so difficult, we spent several hours trying to figure out how to do this, until we noticed that we can transform a for loop into several sequential or parallel statements. So in the end, we didn't even need to slice a for loop, which was very nice actually. And because every for loop can actually use drones from a certain array of drones, we just attach that into the internal sequential statements. But that means we need to understand how we actually slice a sequential statement or a parallel statement using this array of drones. And again, the name of the game here is safety. In the case of the left, we have a definition of the program where the second statement is being executed, but that means there is already a drone that was picked at that point of execution. So instead of sending this to the planner and decide then the planner could decide another drone, we just stuck the drone from the beginning. So the same drone that was moving is the same drone that is going to move after the replanning. We don't want a drone to just flying around without any consequences. And just to show that this works, we actually create a numeric simulation of a multi-drone mission. As you can see, we have here 4 drones moving to different locations. In theory, they were transporting something to nursing homes. And they are actually avoiding red areas. Red areas are dangerous. They cannot fly inside those areas. And the idea of dynamic replanning is at some point, another new area is going to be inserted in the system, and the flight path should change according to that new area. And of course, the drone should not, the mission should not restart. It just should continue from that point. There is something else that I want to talk about here. We are actually working in a very specific domain, in the domain of how we make drones flying around. And we encounter different interesting, you could say small, but the devil is in the details. So the different interesting problems. We are slicing a program using the runtime information of the program. In the case of a multi-drone mission, we have a DSL. The DSL is being sent to a planner. The planner plans. That means the planner is going to generate a flight path for each drone, which is going to be sent to that drone, and the drone is going to fly according to that flight path. The concept of execution of the program and the concept of the drone flying around into the airspace are completely different here. In theory, the program does not control directly the drones. That means we don't have an actually runtime state of the program. So what do we do here is we need to build another system that actually takes every information of the flight path of the drones, where the drones are moving right now. And with that information and the original DSL and the original program, we reconstruct the runtime state. I want to say this because we always take into consideration that, okay, we are going to use dynamic forward slicing, and that's all. When we're working with physical system, we need to do something, be a bit more creative. And with that, we actually managed to solve this replanning problem, which is actually a very difficult problem when you want to rewrite, when you want to solve it in the in the normal way of rewriting the planner or writing a new solver. And we do that by generating a new program using as inspiration dynamic forward slicing. That's my talk.
Are there any questions? I have a question. So it's related to the planner and the DSL you developed for your drones. Is there a mismatch? Have you captured everything what the planner can do in the DSL and vice versa?
I mean, we capture everything because we develop both things together. So we build the DSL and we say, okay, we need a new statement to do something, and then we build how the planner should behave with that statement. The only mismatch could happen with the action of drones. Those are actually defined externally from the DSL, as you know, import actions and stuff like import modules, very similar to that. So in that sense, mismatch could happen. But we don't want to think about that just yet. We want this to work first and then see.
Do we have more questions? Okay, let's thank again the speakers.